Hello, this is Professor Keen, and this is Electricity, Magnetism, and Light. Let's continue our discussion of Coulomb's law. We've been looking at A Student's Guide to the Grade Physics Texts, Volume 3, Chapter 6. In my previous lecture, I gave a detailed description of the torsion balance that Coulomb would use to develop his law of electricity. In this lecture, what I want to do is walk you through the experiments themselves that he carried out. So this is on page 71 in the text, and he describes this in section 6.2.2. Okay, so how does he carry out this experiment? Remember once again the apparatus. Let me jump to that page and just refresh your memory. What he's going to do is he's going to drop this ball. He's going to first of all charge up this ball T that is on the end of this stick. He's going to stick it through this hole right here that's labeled M. It makes contact with ball A, which is down here. And after having made contact with ball A, it transfers some of its charge. Insofar as those two balls are identical in size, they will share an identical amount of charge. So they will both have some charge, let's call it Q, on each of the balls. You notice then that those two balls repel one another. So let's draw a top view. So imagine if you were looking at this apparatus from the top looking down. So this is a top view of the experimental apparatus. And when you do that, originally this rod with the ball on it is in contact with this other ball. This would be the suspension point looking straight down, and then this would be the vane on the end of it right here. And when they make contact, this ball is going to undergo its repulsion, and it's going to move away from the other ball by some angle right here. We'll call that angle theta right there. So these are the two balls right here. That's the one suspended from point M. This is the movable ball. This would be ball, I guess, T, and this would be ball A, which swings around like this to some angle theta. Okay, so let's make a table to describe the data that he collects. Okay, so I'll label this experiment here, and then the angle of the ball A in this column, and so that would be the angle theta. And then this will become more clear as we continue, but the twist, or maybe I'll say this, the angle of the micrometer, right here. And I'm going to make another column, and again, you'll see why I'm doing this in a moment, twist that is in the wire. Okay, so the first experiment he carries out, when the ball is repelled, he says that it is repelled by an angle of 36 degrees. So if he were to look at these markings right here, and he were to look from the outside and look down the shaft of the rod so that you can see exactly what angle that it is at, he mentions that the ball is twisted by an angle 36 degrees. So the 36 degrees right here, that would be the amount by which this ball twists from its initial position. The micrometer, he does not twist the micrometer at the top. Remember, that is the knob at the very top. So he doesn't move that at all. All that really happens, so I'll put 0 degrees here because the micrometer is still reading 0 degrees. That means how much twist is in the wire? Well, originally the wire had no twist in it, but when this ball swings out in this direction, in the counterclockwise direction, CCW, that means in the counterclockwise direction, there is 36 degrees of twist in the wire. In other words, the wire has twisted by a total amount of 36 degrees. Okay? So this is the experiment, or we might say the trial. I guess that's how he describes it here. So that's the first trial. What about the second trial? What does he do then? Well, now what he does is he says he twists the suspension wire through 126 degrees. This is down here at the bottom. He twists the suspension wire through 126 degrees as shown by the pointer O on the micrometer. And when he does so, the two balls approach each other and stand just 18 degrees apart. Okay, so let's look back at the apparatus and make sure we understand what's going on here. So the micrometer at the top here has a point O. What he does is he twists it around in the clockwise direction. And when he does so, the wire is twisting so as to bring this ball A back toward ball T. Okay, and after he has twisted the suspension wire by 126 degrees, so the micrometer is twisted by 126 degrees, and he does that, I should say here, in the clockwise direction. Then what happens is this ball A moves back toward ball T so that now it stands at 18 degrees apart. All right? Now, here's the question I want to ask. How much total twist is there in the wire? How much has the wire twisted altogether? Well, the way you do that is you can add these two numbers together. Why would you add these two numbers together? Well, because if the ball moves away, if it had moved away by a total of 36 degrees originally, there's 36 degrees of twist in the wire. But now when you twist the micrometer 126 degrees back in the clockwise direction, so if the ball was still right here at point A, there would be 126 degrees of twist in the wire. But because the ball is 18 degrees away, it's 18 degrees of twist one way and then 126 degrees of twist the other way in the wire. So when you add these together, you have 136, 46, 44 degrees of twist in the wire. Again, if you're not quite sure why that works like that, imagine you have a rod. Let me give another example right here. If you take your hands and you grab this rod, one hand on the top of the rod and one hand on the bottom of the rod, if you twist the top of the rod, let's say, by 10 degrees that way, and then with the other hand, you twist the bottom of the rod by 10 degrees that way, you really have 20 degrees of twist in that rod. Because the top you've twisted 10 degrees in the counterclockwise direction, the bottom you've twisted 10 degrees in the clockwise direction, but altogether you've twisted the rod by 20 degrees. That's exactly what's happening here. This wire, by the repulsion of these two balls, is twisted 18 degrees in the counterclockwise direction, but the top of it, when you twist the micrometer, that's twisted 126 degrees clockwise, so there are 144 degrees of twist in this wire. Okay, what about experiment or trial number 3? Now what he does is he twists the micrometer, the top, by 567 degrees. And when he does so, and he does this in the clockwise direction, and by doing so, he reduces the angle between the balls to merely 8.5 degrees. So now how much total twist is there in the wire? Well, again, the micrometer has been twisted 567 degrees clockwise. The ball A is repelled from ball T by 8.5 degrees. So when you add these two together, well, 567 plus 10 would be 577. So 576, 575.5. 575.5 degrees of twist is in the wire. Okay, so he collects 3 data points. Now he insinuates that he's collected more data and he's just throwing out a few of the data points that he's collected. It would be nice to see all of the data that he collected. Maybe I would give him, like, a check in the lab or something, an 80%, because he is not showing all of his data. There's a question of whether he's cherry picking his data, I suppose. But Coulomb was the first to do these experiments, and let's see how he interpreted his data. Okay, so if we jump to the next page, he's going to mention here basically what we've been talking about here on the next page, page 72. What he's doing is he's explaining his results. So what is he saying? He's saying, well, this right here is a measure of the distance between these two balls. This is the distance between the charged balls. And this right here is a measure of the force that's exerted by the wire in order to keep it at that distance. Force exerted by the torsion wire to maintain this distance. By this, I mean this distance right here. Okay, so notice what's happening here is that as you apply more and more force to try to push the balls together by twisting the wire, the balls do get closer together. Okay, but let's compare these numbers. In order to go from data point 1 to data point 2, you have halved the angle. So from data point 1 to 2, the distance, at least measured in angle, has halved. So insofar as reducing the angle by half reduces distance by half, that's not exactly correct. I'll come back to that in a moment, but it's roughly halved. Okay? In order to reduce the distance by half, what do you have to do to the force? Well, the force applied must be what? Well, 36 times 2 is 72, and 72 times 2 is 144. So in other words, you have to quadruple the force. Okay? So it takes 4 times as much force to make it half as far away. Okay? What about from data point 2 to data point 3? Again, from 18 to 8.5, well, that's almost 9. So from 18 to 9 degrees, let's say, the distance, once again measured in angle, has halved once again. So again, you half the distance. And in order to do so, well, 144, let's round this off to 576. 144 times 2 is 288. That doubled is what? 576 degrees, or 576. So again, in order to have the distance, the force must be quadrupled. Why does it take this big force in order to push these together? Well, presumably these balls are trying to repel each other with some force. So if it takes a certain force to push them together and hold them at some distance, that must be the repulsive force that they're exerting on one another. Where does Coulomb go with this? He says that this is precisely what we'd expect from an inverse square force. So this implies that the repulsion of two charged objects is an inverse square force. What do we mean by this? The force of repulsion, I'll write this mathematically, is proportional to 1 over the distance squared. Okay, so every time you have the distance, a half squared would be a factor of 4. So it's going to take 4 times. It's going to produce 4 times as much force of repulsion. Okay, so tell you what, I'm out of space here. This is the main result that he arrives at, but if you didn't quite grasp this yet, what I want to do in my next lecture is give a few examples of how this plays out with some calculations.